Hello friends, welcome to Physics by GD. So today we are going to solve the exercise number 11.1 from the chapter number 11 Fourier Series from the book Mathematical Physics by H.K.Dass. So let us start with the question number 1. So question number 1 says that find a Fourier series to represent function pi minus x in the interval 0 to 2 pi. So we know that for representing a function in Fourier series, the general formula is f of x is equals to a naught upon 2 plus summation n starts from 1 goes to infinity an cos nx plus bn sin nx. So whenever the question says we have to find the Fourier series of a function, what we do in this problem is we will first find the Fourier coefficient and we have to substitute this Fourier coefficient in the general formula. In this way, we will find the Fourier series of a given function. So this is the general formula. Here we will find the Fourier coefficient a naught, then an, then bn. Okay. So let us start with our a naught. So the general formula for finding the Fourier coefficient a naught is 1 upon pi integral 0 to 2 pi f of x dx, because here our given interval is 0 to 2 pi. If the given interval is from minus pi to plus pi, then here we will substitute minus pi to plus pi. So the value of a naught is 1 upon pi 0 to 2 pi pi minus x dx. So as you know that the integration of pi is pi into x and the integration of x is x square by 2 in the limit 0 to 2 pi. So when I will put this value and solve this, I will get value of a naught is equals to 0. Similarly, we will find the value of an. So the general formula again for finding an is 1 upon pi 0 to 2 pi f of x cos nx dx. 1 upon pi 0 to 2 pi pi minus x cos nx dx. So I am here splitting the integral. So I am splitting the integral. So it will become 1 upon pi 0 to 2 pi pi into cos nx, pi into cos nx dx, minus 1 upon pi integration 0 to 2 pi x into cos nx dx. Okay, so here pi will cancel out. So I will be left with 0 to 2 pi cos nx dx minus 1 upon pi 0 to 2 pi x cos nx dx. Now the integration 0 to 2 pi cos nx dx and the integration 0 to 2 pi x cos nx dx has some value which is 0 and 0. So how did I came to know that the value of this integral are 0? So here are some basic formulas which you will be using again and again in the Fourier series. So it is better to remember this integral formula for reducing your calculation. So these are the formula. Please take note of this formula because we are going to use these integral values again and again. So there are two ways. Either you use this formula or you can solve again and again by integration by parts. So according to me, this is the easiest way in which you can solve this integral. So please take note of these formulas and please remember this. It will be useful in the Fourier series again and again. So let us start. So the value of cos nx dx is 0 and value of x cos nx dx from 0 to 2 pi is 0. So as you can see in the formula, integration 0 to 2 pi x cos nx dx equal to 0 and integration cos nx dx integration cos nx dx 0 to 2 pi is 0. Okay, so an is again 0. So we will find now bn. So the general formula for finding bn is 1 upon pi 0 to 2 pi f of x sin nx into dx. So I have substituted the value of the function which is pi minus x. Again I am splitting the integration here. So it will give me 0 to 2 pi sin nx dx minus 1 upon pi 0 to 2 pi x sin x dx. Now again I am going to use this integral 0 to 2 pi sin nx dx is 0. So this term is 0 and 0 to 2 pi x sin x dx. So you can see here x sin x dx is minus 2 pi by n. So minus 2 pi by n. So bn is equals to 1 upon pi 0 minus minus 2 pi by n. So it will give me 2 pi upon pi n, which is nothing but 2 by n. So this is the value of Fourier coefficient. Now I will substitute this value of Fourier coefficient in our general formula. So general formula is f of x, which is pi minus x, is equal to a naught by 2. Our value of a naught is 0, value of a n is 0, plus summation n starts from 1 goes to infinity bn into sin nx. So bn is 2 upon n. Okay, so I am taking 2 outside, so I will get for n equal to 1 sin x upon 1 plus sin 2x upon 2 plus sin 3x upon 3. So this is my Fourier series of the function pi minus x in the interval 0 to 2 pi. So now we will move to question number 2. So question number 2 is find a Fourier series to represent the function x minus x square from x equal to minus pi to plus pi and show that pi square upon 12 is equals to this thing. So first we will find the Fourier series of this function. So our given function is x minus x square in the interval minus pi to plus pi. So a naught is 1 upon pi minus pi to pi f of x dx. Okay. So I am substituting the value of function which is x minus x square. Again I have splitted this integral. So the integration of x is x square by 2 and the integration of x square is x cube by 3. So after substituting the limit, lower and upper limit, we will arrive at a value which is minus 2 pi square by 3. So the value of a naught is minus 2 pi square by 3. Now an is equals to 1 upon pi minus pi to plus pi f of x cos nx dx. Substitute the value of function which is x minus x square. So now I am splitting this integral into two parts, x cos nx and minus x square cos nx. So again I am using this formula. So you can see from minus pi to plus pi x cos nx dx is 0. Okay, so this will give me 0 and from minus pi to plus pi x square cos nx dx is 4 pi upon minus 1 to the power n. So an is equals to 0 0 minus this thing 1 upon pi into 4 pi upon n square minus 1 to the power n is equals to this thing. So the value of an is this thing. Okay, so now we will find the value of bn. So bn is 1 upon pi minus pi to plus pi f of x sin nx dx. So again I have substituted the value of function which is x minus x square. So let us solve this integral. So here you can see I have splitted the integral x sin x and x square sin nx. So again minus pi to plus pi x sin x is 2 pi upon n minus 1 to the power n plus 1 which I have substituted here. And the value of x square sin nx dx minus pi to pi is 0. So I have substituted the value 0 here. So bn value is equals to 2 upon n minus 1 to the power n plus 1 because pi has been cancelled out. Okay. So function, so we will substitute this Fourier coefficient in the general formula. So the f of x is x minus x square is equals to a naught by 2. So the value of a naught is minus 2 pi square by 3 divided by 2 plus summation n starts from 1 goes to infinity an. Value of an is minus 4 upon n square minus 1 to the power n. Substituting here into cos nx plus bn. Bn is 2 upon n minus 1 to the power n plus 1 into sin nx. So let us expand this formula. So we will get minus pi square upon 3 because 2 has been cancelled out. Okay, plus 4, I have taken 4 outside, summation n equal to 1. for n equal to 1, sorry, for n equal to odd value, which is 1, 3, 5, these types of value, it will give me minus 1. And here already is minus sign, which means odd value will be positive. So you can see 1, 3, these are odd value and these are positive. And for even one, this will give me plus 1, and here already minus sign is there. So odd, sorry, so for even term we will get minus sign. So cos 2x upon 2 square, cos 3x upon 3 square, and till infinity. Plus here I have taken 2 outside common, so 2, again here odd term will give plus and even term will give me minus, because for n equal to 1 it will be n plus 1, which is 2, so minus 1 square, which is positive. So sin x upon 1 minus sin 2x upon 2 plus sin 3x upon 3 and up to infinity. So this is the Fourier series of the function x minus x square. So in this problem, we have to show that pi square upon 12 is equal to this series. So where square upon 12, we have to show pi square upon 12 is equals to 1 upon 1 square minus 1 upon 2 square. So if I will remove this cos x so if I will convert this cos x cos 2x into 1, then I will get this series na. So put x equal to 0. So in this way this will give me 0 equal to minus pi square upon 3 plus 4 into cos 0 cos 0 cos 0, which will give me 1. So 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square up to infinity plus 2 into sine x sine 0 sine 0 sine 0 sine 0 gives always 0, so it will give me 0. So I will be left with here I am taking pi square upon 3 to the left hand side. So pi square upon 3 equal to 4 into this thing. I am dividing 4 here, multiplying 4 here. So it will give me pi square upon 12 is equals to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square up to infinity. Now let us move to the question number 3. Question number 3 says that find a Fourier series to represent the function f of x is equals to e to the power x for the interval minus pi to plus pi, and hence derive a series for pi upon sine hyperbolic pi. So our given function is e to the power x in the interval minus pi to pi. So again we will find a naught, which is 1 upon pi minus pi to pi f of x dx. Our function is e to the power x, and the integration of e to the power x is e to the power x. Here I have substituted the limit, lower limit minus pi to upper limit pi. So after solving this, we will get e to the power pi minus e to the power minus pi. So we know that this is 2 times sine hyperbolic pi. Okay. So we got the value of a naught, which is 2 sine hyperbolic pi upon pi. Similarly, we will calculate an. So the value of an is 1 upon pi minus pi to plus pi e to the power x f of x into cos nx. Na? So e to the power x cos nx dx. So here I am using an important formula, which is integration e to the power ax into cos nx cos bx dx is equals to e to the power ax upon a square plus b square into a cos bx plus b sin bx. Okay, and integration e to the power ax sin nx dx is equals to e to the power ax upon a square plus b square into a sin bx minus b cos bx. So this is the formula which we will be using here, because when you will solve this integration by part, you will be not able to solve this, because the e to the power x will repeat again and again while derivating it. Okay, so this is the formula which we are going to use here, e to the power x. So the value of a here is 1, and cos nx, so value of b is n. So 1 upon pi e to the power 1 upon pi, this one 1 upon pi e to the power x upon a square plus b square means 1 square plus n square into a, which is 1, into cos bx, which is cos nx, minus, sorry, it will give me plus na. So it will be plus n into sin nx, which is sin bx. So after substituting this value minus pi to plus pi, we will get, so I am taking 1 upon pi, 1 plus n square common. So e to the power pi bracket 1 into cos nx, cos n pi, minus n sin n pi. Sin n pi is always 0, so it is 0, minus e to the power minus pi lower limit into cos minus nx minus sin minus pi is again minus n pi is again 0, so it is equal to 0. So similarly, so in this way, the value of an is equals to minus 1 to the power n upon pi 1 plus n square, because cos n pi gives minus 1 to the power n, and cos minus n pi is nothing but cos n pi, so it will again give me minus 1 to the power n. So here I am left with e to the power pi minus e to the power minus pi. So this is nothing but 2 times sine hyperbolic pi. So 2 and sine hyperbolic pi. So this is the value of an. Similarly, we will calculate the value of bn. So bn is 1 upon pi minus pi to pi e to the power x sin nx dx. Again we will use this formula. So it will give me 1 upon pi into e to the power ax upon 1 square plus n square into 1 into sin nx minus n into cos nx. Okay, substituting this limit, lower and upper limit, we will get this value. So here the value of sine n pi and sine minus n pi is always 0. So here it is 0 and again it is 0. Okay. So this will give me minus n minus 1 to the power n upon pi 1 plus n square, which is common, and the remaining term is e to the power minus e to the power minus pi, which will give me this value. So in this way, I have calculated Fourier coefficient A0, An and Bn. So now I will substitute this Fourier coefficient in the given general formula. So f of x is e to the power x equal to equal to A0 by 2. So A0 is 2 sine hyperbolic pi upon pi. So it will give me sine hyperbolic pi upon pi plus summation n starts from 1 goes to infinity an. So an is 2 into minus 1 to the power n upon pi sine hyperbolic pi 1 upon n square into cos nx. Similarly, I have substituted the value of bn here into sine nx. Okay, so let us expand this series. So we will get 2 sine hyperbolic pi. I have taken common, so here 2 was not there, so divided by 2 and multiply by 2, it will give me same term, plus minus cos x upon 1 plus 1 square, because here odd term will give minus sign and even term will give plus sign. So odd term is minus and even term is plus. Similarly here the odd term will give me plus and even term will give me minus. So you can see, because n plus 1 is there na, so it is odd term is plus and even term is minus. So again we will simplify this. So we will get 2 sine hyperbolic pi upon pi into 1 by 2 plus minus cos x upon 2 5 10 and 2 5 10, similarly up to infinity. In this question we have to show that we have to find the Fourier series, the series of pi upon sine hyperbolic pi. Okay, so you can see here we have pi and sine hyperbolic pi. So somehow if I will remove this sin x and cos x, I will get the value of this thing. So I am putting here x equal to 0. So after putting x equal to 0, e to the power 0 is 1. 2 sine hyperbolic pi upon pi bracket 1 by 2 plus cos 0 cos 0 cos 0. So minus 1 by 2 plus 1 by 5 minus 1 by 10 and up to infinity. Plus every term is sine, which will give me 0. So plus 0. So multiplying pi here and 2 sine hyperbolic pi here, so I am getting pi upon sine hyperbolic pi is equals to 2 times this thing. So this is the series formula for pi upon sine hyperbolic pi. So the question number 4 is obtain the Fourier series for function e to the power minus x in the interval 0 to 2 pi. So the question is similar. So in place of e to the power x, we have e to the power minus x and the interval has been changed 0 to 2 pi. Okay. So always remember this equality sign. It holds some meaning. We will see this meaning in future problems. Okay. So f of x is equals to e to the power minus x, which is from 0 to 2 pi. So we will find first a naught, which is 1 upon pi integration 0 to 2 pi e to the power minus x dx. So after solving this, we will get value 1 minus e to the power minus 2 pi upon pi. Okay. So I have substituted this minus above. So it gives me 1 minus e to the power minus 2 pi upon pi. So an is 1 upon pi 0 to 2 pi e to the power minus x cos nx dx. So here I am using previous formula which I have used there, e to the power ax upon a square plus b square, है ना, a cos bx plus b sin bx, which is n which is minus 1, a is minus 1, a is minus 1 and b is n. So from limit 0 to 2 pi, from limit 0 to 2 pi. So first take the common thing outside, which is pi 1 plus n square bracket e to the power minus 2 pi minus 1 into cos 2n pi plus n into sin 2n pi. Sin 2n pi always gives 0. So it is 0 minus lower limit e to the power 0 bracket minus 1 into cos 0 plus n into sin 0, which is 0. So 0. So after solving simplifying this term, I will get an is equals to 1 minus e to the power minus 2 pi upon pi 1 plus n square. Okay. So similarly we will find bn. So bn is equals to 1 upon pi 0 to 2 pi e to the power minus x sin nx dx. Again using the formula which is here, sin is there, so e to the power ax upon 1 plus a square plus b square a a sin bx minus b sin b cos bx in the limit 0 to 2 pi. So bn is equals to 1 upon pi 1 plus n square. I have taken common here, upper limit e to the power minus 2 pi into sin 2 pi, sin 2 n pi will give 0, so this thing is 0, 0 minus n into cos 2 n pi minus lower limit e to the power 0, which is 1, into sin 0, 0 minus n into cos 0 is 1, which is n. So it will give me bn is equals to n 1 minus e to the power minus 2 pi upon pi 1 plus n square. So again I am substituting this value in the general formula. So I am getting f of x, which is e to the power minus x, equal to a naught by 2. A naught is this, divide by 2, so 2 plus summation n starts from 1 goes to infinity bracket an into cos nx plus bn into sin nx. So an is this value substituted here, bn is this value substituted here. Okay. So let us simplify this term. So we will get 1 minus e to the power minus 2 pi upon pi. So you can see here this 1 minus e to the power minus 2 pi upon pi is common in every term. So I have taken common in. So it will give me 1 upon 2. Here 1 upon 2 is left plus cos x upon 2, cos x upon 2, because n equal to 1 will give me 1 square, which is 2, n equal to 2 will give me cos 2x upon 2 square, 1 plus 2 square means 5, plus cos 3x upon 10 up to infinity. Similarly for sin x. Okay. So this is the general Fourier series expansion for the function e to the power minus x. So question number 5 is, if function f of x is equals to pi minus x upon 2 whole square in the interval 0 to 2 pi, show that f of x is equals to this thing. So we have to find the Fourier series of this function. So the given function is this thing, pi minus x upon 2 whole square. So I am expanding this formula. So a square plus b square minus 2ab, okay, divide by 2, which is 2 square. So will give me 4, 0 to 2 pi. So a naught is 1 upon pi 0 to 2 pi f of x dx. So f of x is this thing. So pi square integration, after integrating we will get x cube by 3 minus 2 pi x square by 2. So I have taken 4 common here, so 1 upon 4 pi, 0 to 2 pi. So after substituting this value, this limit, lower and upper limit, after solving and simplifying this, we will get the value of a naught, which is equals to pi square upon 6. Okay. So an, now we will calculate an. So an is 1 upon pi 0 to 2 pi function into cos nx. So this is function cos nx dx. Now I will split this integral, single integral, into three parts. So pi square I have taken common here, cos nx dx plus x square into cos nx minus 2 pi into integration x into cos nx, x into cos nx. So again I am using this formula here. So the integration 0 to 2 pi cos nx dx is 0, and integration x square 0 to 2 pi x square cos nx dx is 4 pi upon n square, and x cos nx is 0. So it is better if you remember this formula, because here you have to find three integral value, which is very calculative. So it is better to remember this formula. Okay. So after substituting this value, we will be left with an is equals to 1 upon 4 pi into 1 upon 4 pi into this thing, 4 pi upon n square, which is nothing but 1 upon n square. Okay. So now we will calculate bn. So bn is equals to 1 upon pi 0 to 2 pi f of x into sin nx dx. Again I am splitting this integral into three parts, sin x and sin nx, x square sin nx, and x sin nx. Okay. So 2 pi is common, and 4 is common here, 1 upon 4 pi. So this will give me 0, this will give me minus 2 pi upon n, and this will give me minus 4 pi square upon n. You can see the formula. Okay. So after substituting this value, I am getting bn is equals to 1 upon 4 pi 0 minus 4 pi square upon n minus 2 pi into minus 2 pi upon n, which is nothing but 1 upon 4 pi into minus 4 pi square by n plus 4 square by n. So which will give me bn equal to 0. So the so now I will substitute the Fourier coefficient in the general formula. So f of x, which is pi minus x upon 2 whole square, is equals to a naught by 2. So our value of a naught is pi square upon 6, which is pi square by 2 na. A naught by 2 means pi square by 12 plus summation n starts from 1 goes to infinity an. An is 1 upon n square into cos nx, and bn term is 0, so it will give me 0. So this is what we have to show that, and we have shown this. Okay. So let us now move to the question number 6. So the question number 6 says that prove that x square equals to pi square upon 3 plus 4 summation n starts from 1 goes to infinity minus 1 to the power n cos nx upon n square in the interval minus pi to plus pi. And hence we have to show that this thing is equal to this thing and this thing is equal to this thing. Okay. So this is lengthy problem. So we will first find the Fourier series of the function. So the given function is x square. So this x square is even function. Remember this, because interval is from minus pi to plus pi. So we know that for even, so we know that if for integration minus pi to plus pi or plus minus pi to plus pi, f of x dx is equals to, if the function is even, है ना. If the function is even, it will give us 2 times 0 to pi f of x dx, and it will give me 0 when the function is odd, when the function is odd. So I will calculate a naught first. So a naught is not equal to 0, an is not equal to 0, but bn will be 0, because here the function is even, here the function is even, and a naught, and the general formula for finding a naught is 1 upon pi minus pi to pi function into dx. So this function is even, so it will not be 0. So a naught is not equal to 0. Similarly, an, we have function into cos nx. Cos nx is already even function, and we are multiplying with even function again. So it will give me ultimately even function. So the value of an will also not be equal to 0. So we are left with bn. So with the formula for bn is function into sin nx. So the function is even, but the sin nx is odd function. So multiplication of even is even, but the multiplication of odd even is always odd. So the odd function will give me 0 in the limit minus pi to plus pi. So that is why I have written here bn is equals to 0 already. So a naught is equals to 1 upon pi minus pi to pi x square dx. So after solving this, you will get 2 pi square upon 3, and an is equals to 1 upon pi minus pi to plus pi x square into cos nx dx, which is equal to 1 upon pi 4 pi n minus 1 to the power n. This is the general formula which I have mentioned earlier. Okay, this one, x square cos nx, this one, 10th one. So we are getting the value of an is 4 upon n square minus 1 to the power n. So f of x, which is x square, is equals to a naught by 2, which is 2 pi square by 3 divided by 2. So pi square upon 3 plus summation n start from 1 goes to infinity an. So this is an into cos nx. So expanding this, we will get this thing. Odd term will be minus and even term will be plus. So odd term is minus, but even term is plus. So here we have to show that summation 1 upon 2n minus 1 square is equals to pi square upon 8. So I am putting x equal to pi for this problem, first one. So I am putting x equal to pi. So it will give me pi square equal to pi square upon 3 plus summation n starts from 1 goes to infinity 4 upon n square minus 1 to the power n cos n pi. Cos n pi will give me minus 1 to the power n. Okay. So minus 1 to the power n minus 1 to the power n is plus 1. So I am left with 4 summation 1 upon n square. So after multiplying it here, I will get pi square upon 6 is equals to summation 1 upon n square. So you can see, so I can write summation n starts from 1 goes to infinity 1 upon n square is equal to summation 1 upon 2n minus 1 whole square plus summation 1 upon 2n whole square. So this is equal to this thing. Okay, let me give you one example. So how this is equal to, how this thing is equal to this thing, na? So summation n starts from 1 goes to infinity 1 upon n square, na? So it will, for n equal to 1, it will give me 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus 1 upon 4 square up to infinity. So after substituting this value here, RHS, so that is RHS, look RHS. So summation 1 upon 2, so in this RHS term, when I will substitute n equal to 1, this term will give me 1 upon 2 into 1 minus 1 upon, sorry, whole square plus 1 upon 2 into 1 whole square. Now I will substitute n equal to 2. So plus n equal to 2 will give me 1 upon 2 into 2 minus 1 whole square plus 1 upon 2 into 2 whole square, n plus n equal to 3 value and up to infinity. So you can see here This will give me 1 upon 1 square plus this will give me 1 upon 2 square, and this term will give me 1 upon 3 square, and this will give me 1 upon 4 square. So this thing RHS is similar to this thing. Okay. So in this way I have written 1 upon n square equal to this thing. So we have to find summation 1 upon 2n minus 1 whole square. So I am taking this, I am keeping it here, and I am taking this term to the LHS. So it will give me this thing. So as we know that summation 1 upon n square is nothing but summation 1 upon n square is nothing but pi square by 6. So substitute this value, which is pi square by 6, and if you look closely this term 2n whole square na, so divide by 4 and 1 upon n square. So divide by 4, 1 upon n square is pi square by 6. So it will give me pi square upon 8. So in this way pi square upon 8 is equal to summation 1 upon 2n minus 1 whole square. So we have shown the first part. Now we will move to second part. So for proving the second part or finding the second part, we will make use of Parseval's identity. So Parseval's identity is 1 upon pi minus pi to plus pi f of x mod square dx is equals to a naught square by 2 plus summation an square plus bn square. So in this problem our bn is 0. So bn is 0. So this term is removed. Okay. So 1 upon pi minus pi to pi function is x square. So whole function square means x to the power 4 dx is equal to 1 upon 2 into a naught is 2 pi square upon 3 whole square plus summation. This is 4n square minus 1 to the power n whole square an square. Okay. So after solving this integration, and this term will give me this value and this one will give me this value. I am taking 4 common here, and minus 1 to the power n, and square of that thing will give me, this will give me 1 plus 1, and 4 square will give me 16. So I have taken 16 outside. I have been remain with summation 1 upon n to the power 4. So summation 1 upon n to the power 4 is equals to this thing minus this thing. So this thing minus this thing. So if you solve this integral, you will get this value, and this will, and it is giving me this value. So after solving this value, I am getting 8 upon 45 pi to the power 4. Okay. So 60 multiplying 16 here, so it will give me, cancel out, it will give me 1 and it will give me 2. So it will multiplying 2 here, I will get summation 1 upon n to the power 4 is equal to pi to the power 4 upon 90. So in this way you can show 1 upon n to the power 4 is equals to pi to the power 4 upon 90 by using Parseval's identity. Okay. So now let us move to the question number 7. If function is periodic function defined over a period 0 to 2 pi, and the function is this, we have to prove that function is equals to this thing, and also show that pi square upon 6 is equal to this series. So same thing we are going to do. The function is defined in the interval 0 to 2 pi. This is the function. So a naught is 1 upon pi 0 to 2 pi function into dx. So this will give me 3 into x cube upon 3 minus 6 pi into integration of x is x square by 2. I have taken 12 common outside. 2 into pi square into x. After substituting the lower and upper limit, I will get a naught equal to 0. Okay. So now let us find an. An is 1 upon pi 0 to 2 pi function f of x into cos nx dx. Again I am splitting the integral into 3 parts: x square cos nx, x cos nx, 2 pi square cos nx. So we know that this value is 0, this value will give 0, and this will give me 4 pi upon n square, again using this formula here. Okay. So I am getting an is equals to 1 upon n square after substituting the value, which is 3 into 4 pi upon n square. So I am getting 1 upon n square. So let us find Bn. Bn is equal to 1 upon pi 0 to 2 pi function into sin nx dx. Again splitting this integral into three parts: x square sin nx, x sin nx and sin nx. Okay. So this term is equal to 0. This term is equal to minus 2 pi upon n, and this term is equal to minus 4 pi square upon n. So 1 upon 12 pi, 3 into minus 4 pi square upon n, minus 6 pi into minus 2 pi upon n. So this will give me 0, because this thing and this thing are same, so it will give me 0. So Bn is equals to 0. So my function f of x is summation n starts from 1 goes to infinity cos nx an into cos nx. So an is 1 upon n square, because a naught is 0 and bn is 0. So I am left with this thing only. Okay. So which we have to prove now. So we have proved this thing. Now we have to show this pi square upon 6 is equal to this thing. So after putting x equal to 0 in this equation, I will be left with f of x equal to 0. So x equal to 0, x equal to 0. So this two term will be 0, and I will be left with 2 pi square upon 12 equal to 1 upon n square cos x na cos x cos 2x cos 3x. All thing will give me 1 1 1. So in this way, pi square upon 6 is equals to this thing. We have shown this thing also. Okay. So this was our exercise number 11.1 from the chapter number 11 Fourier series. So that's it for today's video. So if you find this video helpful, so guys, please like, share and subscribe. Thank you for watching.